All right, welcome everybody. Welcome to this week's webinar, this month's webinar. We have a guest presenter this week. So this is Dr. Caroline Hain. She's a postdoctoral researcher at EMPA in Switzerland. And she's an expert in material sciences with plasmas and with plasma diagnostics as well added in there. Her primary research topics all involve deposition, in particular, metal sputtering with high PIMs, reactive high PIMs. She looks at diamond-like carbon coatings as well, and also works with on process development with PEALD. Today she's going to talk about her work in the lab using like developing and optimizing different thin films and different surfaces and the properties of the surfaces. Using plasma-enhanced processes and using plasma diagnostics to help guide the research to get the optimal material properties. So with that, Caroline, take it away.
Thanks, Tom, very much. And so welcome everybody to the webinar. So for those that are joining for the impedance webinar, welcome. We also probably have some attendees for our plasma coffees. So as Tom mentioned, so today I'd like to present a bit what is possible when we couple plasma diagnostics with our deposition process, what kind of information we can gain from there, and then how we can use that information to then tailor our films. Right, so this is the motivation, right? So we have a material we want to deposit in the form of a thin film, right? And then for it to reach or to attain the correct properties or the desired properties for a specific application, right, which can range, right, from hard coatings like wear-resistant coatings, optoelectronic, hydrophobic, all kinds. Then we need to meet these specific requirements already, starting from our substrate to film interface, so looking at conformality, substrate response, nucleation, diffusion processes, continuing to film growth. So then seeing how what kind of growth mechanism we have, the growth rates, homogeneity, chemical composition, purity, microstructure development, porosities, defects, all these phenomena. And then, of course, we look at the end product, so our our surface of our film. So there we can also look at aspects related to surface roughness, the morphology, chemistry. So these are different things we need to take into account. So to do that, we want to somehow enhance or to have the possibility to control these different aspects. So this is, say, a small example of the type of research that I've been working on. So the idea is that we want to give ourselves the possibility to characterize our deposition environment. And so then we can understand how our process parameters, the ones that we're actually able to turn, how those affect the deposition environment, and then in turn, how that affects the properties or the structure of our material. So the system that I've worked with quite a lot, so over the past few years, is with a Corvus system, which is quite nice because it has this modularity, so you can nicely adapt it to different processes. So for instance, what is possible, or the type of research that I'm working on, is that I look into magnetron sputtering, so primarily high PIMs. So it's the context of the webinar today. And so the idea is that we have a localized plasma at the magnetron, right? We sputter a material, which then travels towards our substrate. And from there, let's say we have few possibilities for tuning, right? So also, for instance, having a substrate bias, we can try and affect our charge species, and we have just atoms, then we can't do so much. But we can also introduce other plasma sources. So in my case, I look into microwave plasma, which can then fill the volume of our chamber. So we have these two plasmas which can interact with one another. So for instance, our sputter species can be post-ionized. So the atomic species that sputter can be ionized in this microwave plasma, or we can introduce, for instance, reactive gases. Right? So then the microwave plasma acts as a source for exciting, for ionizing, or dissociating reactive gases, so that we can get, in turn, a stoichiometric compound. But besides looking at different processes, right, depending on what you need and also what you have, right, you have different options. But now we need also a way to understand what's happening. And also for this, we have a range. So how? So for this, we have range. So this is just a few toys that we can use to try and understand our system. So in the context of HyPIMS, then we can look at the change in their current waveforms and how that's developing within a pulse, because HyPIMS is a pulse process. We can use optical emission spectroscopy to look at the type of species that we are producing. So we can look at the atomic species, excited, also molecular ionized. Then with the Langmuir probe, what we can do is that we can look at the plasma properties. So we can evaluate the plasma potential, floating potential, plasma densities, electron temperature. Then with that, we can also move on to putting in a crystal microbalance. With that, you can measure deposition rates. With the quantum system from impedance, then you have this modified quartz crystal microbalance that it's coupled with a retardant field analyzer. So with that, you can look at, or you can decouple when you're measuring the neutral species coming in and the ionic species and how they contribute to your film. And then also we'll have examples of a time of flight mass spectrometer. So with that, we can evaluate the chemistry. So what species are reaching the surface of our substrate. And then in this case, it's an energy resolving time of flight. So not only can we characterize who is reaching the substrate, but then also with what kind of energies when we talk about the ionic species. So why is this important, right? So also if you look through literature, then there's a lot of information available, right, in terms of just sputtering, of just characterization of the developed films, right, on plasma diagnostics itself. But then the idea is that we take all these different information, right, each is a single piece of a puzzle, and then we start to put together, we can get let's say a big picture, or to understand really from start to finish, right? So from our, let's say, which parameters we select, how that then influences our deposition environment, and then what kind of materials we're able to produce, and then tune them for specific applications. So if we put it into the context of HyPIM, so the information that will give you can also be, let's say, transferred to other deposition systems. So in this case, it will be mostly focused on HyPIMS. So why can it be useful in this context to use plasma diagnostics? So first I'll start with a small, or for those that are not familiar with, explain a bit what HyPIMS is, and then you'll see why we can use plasma diagnostics to really understand our process. So if we look at it, let's see, at this in the time scale and also the power that we apply. So if we first look at direct current magnetron sputtering, right? So what happens is here is that we have a continuous sputtering on time, so 100% duty cycle, and we have peak powers, let's say, of 0.1 to 1 kilowatts, and so we continuously sputter. Then we can move on to pulsed systems. So we can do pulsed DCMS. Right? So now we're talking of frequencies up to 100 kilohertz, right? So the on time is a few milliseconds in this case. And depending on the frequency, then our duty cycles can be between 10 to 90%. And with that, the peak powers are between 1 to 10 kilowatts, maybe somewhere around that. Right? So it comes in these pulsed packages, right? So this would be the on time. And then the next step is high power impulse magnetron sputtering, so HyPIMS. So here you can see that if you look at the on time is just really, it's in the microsecond range often, with duty cycles of maximum or in the range of 5% or lower. And here we can get much higher peak powers, right? So up to even 100 kilowatts, right? So, and then to put this a bit maybe into context, so in my work on diamond-like carbon there, we did pulsed DCMS and HyPIMS. So here are just the conditions. So we had the pulse off time, so 0.4 microseconds, that when it was off, a repetition rate of 100 kilohertz, and a constant, so this a constant sputtering power of 300 watts. Here's for HyPIMS, the pulse onsetting was 30 microseconds at 600 hertz, and then we had the voltage set at above 900 volts, and then we reached the peak current of 30 amps. So now if you look at, let's see, the output. So if you look already at the duty cycle, so here we had 96%, right? So almost continuous, whereas here it's 1.8. And now it's more interesting if you now look at the average pulse power, right? So for pulse DC, then it's 312 watts, whereas the average power for high PIMs, then it's 5,000 watts. Right, and then of course you can calculate from there the pulse energy, which is also significantly higher for high PIMs. So what does that mean? So if we compare these two, then with high PIMs, we can reach high plasma densities. So here we have 10 to the 19th cubic meter here, whereas compared to DCMS, it's 10 to the 16th. Right, so we have an increased probability of ionizing collisions, higher degree of ionization of our spotted material. Right, so here we have some examples. So it's for titanium, aluminum, copper, and carbon. All right, so here we have the electron density, which we can so extend to the ion density. All right, so for DCMS, then we're in this low or relatively low range. Also, you look here at the ionized flux fraction. Right, it's very low in comparison to what can be attained with high PIMs. Right, and then one of the techniques, optical emission spectroscopy, which I'll also talk about a bit later, then we can see here that for DCMS, we mostly have atomic states, ground states, whereas with high PIMs, we're able to identify that we're producing titanium ions. So why is that interesting? So when we start to generate a lot of these so ionized species, so they have a charge, so we can control that charge. So then we get, say, an extra dial or an extra parameter that we can then use to tune our deposition process. Right, so for instance, here we can deposit into trenches, we can by applying a bias. Yeah, so the neutral species will just fall into, let's say, a trench, like here, whereas we can actually, with applying a bias here, we can attract our ions towards the surface, right? So here we have a comparison between DCMS and high PIMs. And so here we can see that the columns are rather, let's say, at an angle, whereas with our high PIMs, we have a nice compact film. Right, so and here's another example. So actually for some colleagues at EMPA. So here they were looking at depositing aluminum nitride. So they compared it with DCMS with a constant bias, right? And then since most of the species that are coming in are atoms, and they won't be affected by the bias, so they just say it's a line of sight. So they will grow in this kind of angled structure, like so. And then with high PIM, since we have a lot of ions around, right, we can attract them in a specific direction. And what we can also do, so when we generate ions, so of course, if in the context of aluminum nitride, then we have aluminum, we have atomic and molecular ionic nitrogen available, neutrals, and then we also have argon ions. Now, argon ions, what they can do, they can actually cause downward defects. They can get integrated into the film, or when they're bombarding with high energies, they can cause unwanted defects within our material. So what we can do is that we can actually tune, for instance, when we have the bias on, when it's off, so only attract the species that we're interested in. So in this case, it would be for aluminum. So if we look in detail, so this is what's the structure of the film looked like, or the orientation of the grains for DCMS, so a continuous bias with few ions available to actually control. And so it's quite polycrystalline, right? But, or we have grains in, let's say, differently orientated here, but now with what they call, so it's metal ion synchronized high PIMs. So what they do is that they only attract the metal ions, so when they know that they're coming, and they were able to grow here a very nicely orientated aluminum nitride film. And so these are the kind of possibilities that we have. So with that, so with controlling the ions, we can influence the structure of our material. So this is something that is, let's see, well known already. First, it was Thornton's, and so already 50 years ago. So he developed the structural zone model. So just briefly, that Of course, this is just to give an idea. It's never like one-to-one, but to kind of orient it yourself what kind of structure you could possibly obtain. And so here it's as a function of our pressure inside the chamber. So this is for argon, so our inert gas, and then as a function of the substrate temperature. So it's actually a ratio between the substrate temperature and the melting point of the deposited material. Right, so you have these different zones, and then we can go for something porous, right, tapered to more columnar grains. But now we want, or since then, considerable work has gone in, and we actually have, let's say, a more updated structural zone model. So this was developed by Anders in 2010. So this model, so it builds up on the previous one, but to incorporate also our plasma-based phenomena, right? So then here it actually highlights that we need to take into account energetic bombardment during our film growth. So in this case, what happens is that, of course, we have our thickness because it also incorporates etching in this model. But now instead of our temperature, our substrate temperature here, what we have is a generalized temperature. So what it does, it accounts for the heat supplied by incoming particles, potential energy. Right? So with this, the potential energy, then it's linked with the cohesive energy and the ionization energy. Right? So that means it's not applied to neutrals. Okay, and then the other aspect, so instead of having pressure now taken into account, you have this so-called normalized energy. So it considers the incoming particles' kinetic energy and its role in displacement and causing heating effects. So when you think of kinetic energy, what you can think of is, say, the acceleration of these particles inside the bulk plasma and sheath acceleration, right? So we have our components from the ionized species, right? So from their energy and the kinetics. Okay, so if we put this then, let's see, into some examples. So this is an example of copper. And so these films were sputtered using different substrate biasing, so from grounded, right, and using several different voltages, so 60, 100, and 130 volts. And then we can see that by changing this substrate bias, so with that, changing the energy of the incoming ions, we can significantly change the morphology of our copper film, right? Going from these rather small grains into these more, let's say, mounds, right? And then if we compare with DCMS as well, so there's high PIMS and DCMS, right? Then we also have more possibility for tuning this grain size in comparison to DCMS, right? So what we can see here, for instance, that when we use these the higher negative bias voltages, we can increase the bombardment or intensify the bombardment with copper ions. And then we can also, with that, enhance the surface mobility. So that's just, so morphology is one aspect. Then we can also look at the stress development, right? So then we can control, depending on the applied substrate bias, with that the energy of our incoming ions, we can tune the stresses in our film. And so, so depending again on the application, then we have this, let's say, this parameter that we can tune. Then if we look more at the applicational aspects, right, so for copper, right, then it's interesting to be able to control the grain size. So if you look at here, so this is the comparison between DCMS and high PIMS. So we have this size-dependent effect, right, is that we're able to control the resistivity or affect the resistivity. So what happens is that, so if you look here, that with high PIMS, we're able to get larger grains, or we can tune to have larger grains, right? So with larger grains, then we have a lower grain boundary density, right? So we reduce the scattering of free electrons, right? So we can see here, if we have small grains, then we have these many grain boundaries, and to travel across with larger grains, we can avoid this. Okay, so that was a bit more on, let's see, brief introduction into high PIMS. And now, apart from how can diagnostics be useful for high PIMs? What kind of information can we actually get from these plasma diagnostic tools? So another, let's see, advantage of high PIMs. So apart from what we spoke about before, so this high plasma density in comparison to DCMS, we also have some additional flexibility or additional parameters that we can steer. So that is the pulse width and the pulsing frequency. And so here, this is on the example of copper, aluminum, zirconium. So this was done by Leo, who at the time was a master's student with us. Currently, he's doing his PhD at EMPA. So he worked on this ternary system, copper, aluminum, zirconium, and then he studied the effect of different pulse widths. And so for 25, 50, and 100 microseconds for these three different metals. So how can you look at these, or how can you try to understand what's happening when we change the pulse width? So we can get these current waveforms like we see here, so by using an oscilloscope. And then we can also see what happens to the deposition rates, right? So when we compare the neutrals and the ions, right? And then from there we can get the ionic flux fraction. And so this is the quantum system, the modified quartz crystal microbalance. So from the oscilloscope, we can get the waveforms. And now we can look first at what's happening with the deposition rate. So this is for the three different pulse widths. And then here, so the dashed areas, then that's the neutral contribution. And then the full bars, then that's the ionic contribution. And so if we look at silver, so this blue, then what we actually see is that we only have neutrals. We don't actually produce any ions. Now, if we look at copper and zirconium, so in all cases, we produce neutrals and ions, but that ratio, it changes depending on the pulse width that we use, right? So for instance, for copper, we have an increase, right? And the number of produced ions versus atoms or neutral species. And whereas for zirconium, it decreases, right? So if we look here, so indeed, so this ionized fraction, and then with increasing duration of the pulse, then the ionized fraction decreases for zirconium. For copper, it first increases quite significantly from 25 to 50 microseconds, and then decreases once more when we increase the duration of the pulse. So I will put in one example. So on copper, how can we characterize this behavior? For more details, then I have backup slides in case there's some questions later, or you can also check out the paper. So if we look at copper, right? So it reaches, let's see, a peak value, a peak current, right, around this 40 microseconds. And then once we increase it, it stays, unlike the other ones, right? So it's stable. So what happens there if we now go back or go to these tables? So we have the ionization energies for their three different metallic species plus argon, right? So then we have the energies necessary to reach, let's see, so singly charged, doubly charged, and the work function that's necessary. And then we also have some discharge relevant properties. So what's the sputtering yield when we sputter with argon ions, when we have self-sputtering? So for instance, if when copper is sputtered by copper, the thermal conductivity of our metal and the melting points. So all these aspects will affect the discharge. So in the case of copper, then we can produce many doubly charged species, and they can contribute quite strongly to the generation of secondary electrons. So we have a lot of extra electrons present to sustain the discharge. And in the case of copper, what happens is that it enters the self-sputtering regime. So with self-sputtering, so we then, in this mode, right, so we're sputtering copper with copper. But even though we are able to reach high ion densities with this copper discharge, as we can see here from the results, we don't actually increase the ionized fraction, we decrease it. So what happens is that for these longer pulses, is we have so-called back attraction, right? So that means that the sputtered ion or the ionized species, they then get attracted back to the target, right? So then that can be caused by the high electric field, the target, when we have our plasma, so during the pulse on time. So this is also one of the reasons why with hypens we can have lower deposition rates, one of them. So then apart from having, so we have all this information from our diagnostics, right? So we can understand what's happening during the pulse of these different metals and then for different pulse durations. And so then when we start to produce our materials, right? So depending if we're looking at something which is a copper rich, zirconium rich, with high, low amounts of silver, depending on the pulse width, right? So we go from 25 to 50 to 100 microseconds, we can actually induce quite significant changes in our material, right? So we can go from something, so we can change the crystallinity, right? To go something more amorphous to actually crystalline, right? Then we can also have either a very porous material or can have very compact films with smooth surfaces. So by then linking the information that we gain from our in situ diagnostics, we can actually tune our films. Okay, so for another example, then I move to diamond-like carbon, right? So in terms of characterization, it can be a bit tricky. In terms of DLC, if we have something more sp2-like, sp3-like, right? So more graphitic or more like diamonds. So in this work, I was looking from pulsed DCMS to hypens and then microwave-assisted hypens. So here I'll focus on the examples of comparison hypens and microwave plasma assisted hypens. And so we have our carbon targets here, we sputter. So in the first cases, we did a continuous substrate biasing. So the bias is always on, right? And then for the same bias, these are the two, films that we got. So with and without the microwave plasma. So in the first case, without microwave plasma, then we have this kind of granular cross-section and quite granular also morphology. But this is even more so the case with the microwave plasma assisted process. And then when we look at the mechanical properties of this material, then for just hypens, then we were getting hardness around 25 gigapascal, right? Which then significantly dropped for the microwave plasma variant, right? To below 10 gigapascal. And just if you want a hard coating, this is not good. So then how can we understand what's happening during our process? So with this, we can use our plasma diagnostics, right? So we can look, of course, at the waveform. Then, so in this case, it's 30 microsecond duration. And one tool that we can use is Langmuir probe. So essentially, it's a metal wire that we put in. We apply a voltage. We do a voltage sweep, and then we see how the current changes. And from that, we can extract different information. I'll show in a moment. So we place the Langmuir probe at the height of our substrate. And then with this, we can look at the development of the plasma potential, the electron temperature, and the plasma density, so the ion and electron densities. So if we look first just for hypens, so this green area marks when the magnetron pulses on, so these 30 microseconds. Right, so we have an increase in our plasma potential, so it's around, let's say, 4 volts, right? For the electron temperature, we reach something of 3 electron volts. And then for the ion and electron density, we can see that the maximum, let's see, the peak approaches just after the pulse. So we need some time after the pulse is ended for the species to travel towards the substrate and be detected. Right? And otherwise, when we don't have the plasma on, then we don't measure much because there's nothing to measure. But now, interesting, when we look at the microwave plasma variant, right? So the microwave plasma is always on. So we first measure the properties of the microwave plasma, which are stable. And we can see here. Then we have the pulse on, and we can see that actually all our species, so our plasma potential drops here. So electron temperature, we also have a dip in our ionic and electron densities. But then after the pulse, then we revert back to the states of the microwave plasma, except when we look at the plasma density. So for the ions and electrons, we have an increase after the pulse. So what's happening here is that when we have the magnetron plasma on, right? So we have this, so we generate a magnetron trap, right? So the electromagnetic fields trap the species. So first they get attracted by the very high negative voltage, and they get trapped in this area. And then after the pulse, so after we no longer have this field present, they are able to travel back towards the substrate. So now we have the information of when the ions are actually, or the most of the ions are reaching the substrates. So now we can use that information. So similarly, like shown on the example for aluminum nitride, we can do synchronized biasing. So we only have a bias when we know those ionic species are reaching the substrate. So then how did that change the material that we got? So this is with the pulse bias variant here, this last one. And so we can see that our film has a more columnar growth, and we have quite a smooth surface of the produced diamond-like carbon film. And we reached similar mechanical or similar hardnesses as to the variant without microwave plasma, but we were able to, let's say, further work on or to improve the surface of our film. So we're able with that to increase our the level of control we have over our process. Okay, so now another example. So let's say extend in complexity. So these kind of diagnostics can also be used for reactive sputtering. And just a quick recap for reactive sputtering. So it would be to create a compound. And so you can sputter directly from compound targets, but then that can often be quite tricky because they're often non-conductive. So you are mostly limited to radio frequency sputtering, right? Whereas another possibility is to sputter from a metallic target and introduce a reactive gas. And then we can produce here a compound, but the reactive gas doesn't just react with what we've sputtered or what's on the substrate, it reacts with everything, so also our target. So when we create a compound layer on a non-compound target, so it's so-called poisoning effect, we can actually change the properties of the discharge conditions. So there are also information available in literature for oxides and for nitrides. So this is in the case of when we bombard then our nitrated surface with argon. So I was working on indium nitride. If you look at indium nitride, then it has, so this is what it shows here is the change in the secondary electron emission yield upon nitriding. So in the case of indium, it drops quite significantly, so about 40%. So if we look then at the numbers, we would need approximately 17 ions, or that 17 ions are lost to generate one electron. Right? Whereas for indium, then it's more than doubled. And I think here we only need 3 ions, or the only 3 ions are lost for the generation of one electron. So from there, we already see that we can have some problems with our discharge. Right? So this is again with the microwave plasma on, we introduce our reactive gas, and here we have our indium target, and we sputter. So we go back first to our current waveforms, right, that we measure with the oscilloscope. So this is just when we sputter with argon, right? We get this nice waveform shape. So this is for a pulse duration of 25 microseconds. But now what happens when we introduce a reactive gas? So what happens is that we have these so-called time lags, right? So there's a delay in when our current actually develops or when our discharge develops. So this time lag, so it's in other words, a delay in the current onset. So it's a contribution of, let's say, what's called a statistical time lag. So that's the time needed for the initial electron to appear in the electric field, and then a formative time lag. So the time which is needed for the discharge to develop from the electrons. And so we know that we have a drop in the secondary electron emission yield. So we don't have enough electrons present to start the discharge. And this is what we see in our waveforms, right? We have a delay. And then we can see that first for, so without microwave plasma, we have this delay. Then for low microwave plasma powers, it increases. But when we increase this microwave power, it actually goes back, and we once again have a stable process. And then another method that we can use to try and understand what's happening at our discharge. So we can use optical emission spectroscopy, and we can identify what kind of species are generated. Right, so of course we can look at indium states, so atomic indium, ionic indium. But what's interesting for us is to look at nitrogen species. So here we can look at the molecular nitrogen species, molecular ionized, excited, and also atomic nitrogen. Right, when in sense of reactivity, then when we have these different excited states, then we can actually start to have these chemical reactions, because molecular nitrogen itself is inert. It doesn't like to react. So we need a way to get it activated, excited, to ionize or dissociate. But besides being able to identify what species we have there, we also have these so-called potential curves. So that can give us additional information into what's happening, right? So what we can do is that we can follow the transitions in our state. So, or for instance, if we look here, we can learn about, for instance, the ionization energy required to go from molecular nitrogen to ionized molecular state. So we look at the ground state. So there would be about just under 16 EV required to ionize molecular nitrogen. So we can get some information about what energies could be inside our chamber at that time. Then what we can also do is that it's very difficult to make OAS quantitative, but we can look at it in a qualitative way, so we can establish trends. So in our case, that we saw that with increased nitrogen flows, we had a drop in the indium ion signal, and because the target's getting more poison, or we're not developing as many ions. And then with the increase in microwave power, we're generating more atomic nitrogen in comparison to all other nitrogen species, which is then beneficial if you look at the terms of creating a stoichiometric film. So with that, we can shortly summarize to understand what's happening at the magnetron or the discharge conditions, right? So when we go into reactive sputtering, so using these current waveforms in OAS, what we can understand is that with just argon sputtering, we have a stable process, we have enough electrons present, no problems. But when we introduce nitrogen, we start to create this delay in the current onset, right? So we're creating reactive nitrogen species, which react with our target. Then we have a drop in the secondary electron emission yield, so we don't have enough electrons present to sustain the discharge. When we add microwave plasma, so first is low values, we actually increase our time lag. So we're creating in the microwave plasma more reactive nitrogen species, which are then able to react even more with our target. And even though it's also a source of electrons, there are not enough present to kind of counterbalance this reactivity. But once we move to much higher powers, then we have sufficient number of electrons there present that we can start the discharge without any problems. And then for my final example, so still staying with reactive sputtering, but now moving to zinc-tin nitride. So here we did, first, similarly, like with indium, we wanted to understand how it behaves when in contact with nitrogen. And it behaves very similarly, that we create these time lags. So this, we understood that we can move to higher microwave powers to revert this effect. But now we want to understand more, right? So what's happening really on a chemical level, what species are reaching our substrate? And for this, so we used a time-of-flight mass spectrometer, but this is energy resolving. So that means apart from the TOF-MS, then it also has an electrostatic sector analyzer, where we can, tune what energies or which species with a specific energy reach the TOF. So we can characterize who's arriving with what energies at the substrate. Right, so we would have it then installed on our plasma chamber, and here's where the ions would travel through. So with this, we can only look at ions. and still it gives us information. So this was developed within the frame of a project from TOFWork. We're actually just down the road from our facilities at EMPA in Thun. So what information can we get there? So there are different ways of presenting the data for sure, but here we can look at these contour plots. So what we can get, so this is in case of sputtering tin. So we have our energy per charge, right? This is the time of our discharge. So look here, so this would be the time. And then we also get the ionic flux. So this is in the case, so we have argon ions, molecular nitrogen ions, atomic ionic nitrogen ions, tin. But also interestingly, we're able to also identify tin nitride species. So with 1 nitrogen and 2 nitrogens. So the benefit of using the TOF is that we over the QMS is that we can get the full mass spectrum. And then we can also follow the isotopic profile if a given element has this type of profile. So with tin, indeed it has. So this is for tin, right? So for 120 Thomson, has this profile that we can follow. Then we add 1 nitrogen here. Then we see that our mass shifted by 134, right? So the whole profile shifted. And then we added another nitrogen, and again, the whole profile shifted to these higher masses. So we can really identify this is indeed tin nitride. Then we can do the same for zinc. And so we also identified zinc nitride species that are reaching the substrate. Another interesting information that we gain from the TOF-MS, so looking at the ionic flux and then the energy per charge, that we can see that, so this is, again, this would be the time frame of our Hypens pulse, and then this is with the microwave plasma on. And so most of the ions come in with a small range. So here it's around 2 volts, so it's the energy per charge, so around 2 volts, right? So with that, we're able to control the energy of most of the ions, right? So rather than having this very spread out tail, right? So for instance, for some Hypens conditions, it can be from 5 to 20 or to 30 volts. Here we have a very narrow energy distribution. So then once we have this information, what can we do with it again in terms of our material? So we can deposit films. So here we deposited using different microwave powers and substrate biasing from floating grounded to -25 volts. And so all the films had a very similar chemical composition. And then we can see that from going from floating to a biased sample, then we're going from a polycrystalline film into something that's more preferentially grown. Right? And then if we look actually at our films, so from SEM, so for floating, then we would have energies of around 5 volts and 7 volts, depending on the microwave power applied. Right? We have something, so if you look at the surface morphology, it's quite, let's say, it's cauliflower structure with many pores. We can also see this in the cross section where grains are rather tilted and also so conical, and we can see these porosities throughout. Then we move to grounded. So we shift the energies to 10 and 12 volts. Right, so now we have this more rice grain surface morphology. The columns have gotten straighter, although some are quite still discontinued with some porosities visible. And then we move to our biased sample. So now we're shifting to energies of 35 and 37 volts. And so now we have a very compact film, right? We also have very straight grain. So we have this growth so continued from the substrate until the top to the surface. And then what we can also see is that between these two samples, it's a difference of 2 volts by applying these 2 different microwave plasma powers. Then we're able to produce smaller grains. So for the 37 volts, which is also reflected in our XRD pattern by the slight broadening of our peaks. So by using the information from ETOF-MS about the energy of our ions, we're able to tune the structure and the morphology of our material while having the same chemical composition. So to just summarize briefly, so with Hypens, then it's a type of magnetron sputtering process. We can reach high plasma densities, and with that we have a high ionized flux fraction, which we can then control since it has a charge. Right, so we have these various knobs that we can tune for our deposition process. Now, in terms of understanding your process, then it's important to find the deposition environment. And so looking at the plasma properties, the type of species which are developed, and then we need to know what parameters are available that we can tune, how that influences the deposition environment, and then we can link that to the properties of our fabricated films. And there are many diagnostic tools available. And so some of them I mentioned. There are others that are in situ, which are linked to characterizing the film, like in situ ellipsometry. I can do in situ stress measurements. Yeah. But it's also important to understand what information you can gain from them, right? Where this information comes from, where do we get the numbers from, and then also what you can then in turn do with the data and how you can apply it to your process. So with that, I'd like to thank you very much for listening. And now I guess we open the Q&A section, so which we would do together with Tom.
Thank you very much, Caroline. I forgot to mention at the start of the presentation, there's a little Q&A box. So if you want to type questions, type now and we'll answer them together. Just before we get to the questions, a lot of our audience is really from like also from the semiconductor background and using plasma sources that are like RF or, different to high PIMS and pulse DC. But I think what you were showing there, it's actually applicable. I want to say the interaction between the fundamental parameters and the surface properties is true no matter what the source, right?
Sure.
Whereas with high PIMS, you get the advantage of the super high density, super high ionization fraction, and like you said, you can control the synchronization, so you can, remove the contaminants like argon getting into the surface. But a lot of these are really broadly applicable, actually.
Yeah, I mean, it all depends in the end what you need, right? What's available. But let's say the concept, then it remains quite similar throughout different deposition processes.
Yeah, like you were showing at the end there, how like even a fairly small change in ion energy going from floating to grounded and then grounded to a small bias already changes the material properties, because it can be at these low energies where you reach that etching threshold, right?
Yeah.
So you get some different things. And also, if you kind of multiply the ion flux by ion energy, it's kind of like the power being deposited. So again, going back to that Anders diagram, you get different local heating effects on the surface with the different power being deposited.
That would be here.
Yeah, exactly. So like it's really nice to see the reality of this diagram in your, you have your diagnostic results linked then to the real material properties at the end. So I will let me open up the Q&A box. So we have a few questions there. Bob asks, will the presentation be made available after the webinar? Yeah, after the webinar, we usually send out a recording. It's usually the next day. So we'll talk afterwards, Caroline, if we can distribute the slides.
Sure. For me, it's no problem. Yeah.
Okay, perfect. We got a question regarding slide 23, which is on the Langmuir probe data.
Yes, let me go to 23. So I guess it's how the Langmuir probe surface coating with. So in the sense of how it was, I mean, yes, if we put in the Langmuir probe and then we sputter, then we coat also our Langmuir probe. So we would only have the sputtering process on while we were measuring to try and reduce this as much as possible. There's also an option for doing, let's say, in situ cleaning. So that's using impedance Langmuir probe. We have this option. And of course, at some point, you have to take it out and change the tip, because it will affect in the end your values. So that's why you always have to monitor the numbers if they make sense or not as you're continuing your measurements.
The next question is, where was the Langmuir probe inserted relative to the substrate and magnetron? I think you had that in it. That's actually in that diagram there, right?
Yes, so here then it was, so we put it at the height of the substrate. So for these tests, we removed, like, not have the silicon wafer in place, but we put our Langmuir probe. So it was, I think it was about 10 centimeters from the magnetrons, and then in the place of where the substrate would be.
It's possible to always measure exactly where your substrate is, right? Because
Yeah.
anywhere else, you still have to make an
Yes.
inference to where it's
Yes.
going to be. I
Yeah.
think for your TOFs measurements, you also actually at the TOF entrance at the
Exactly.
substrate position, right?
Exactly. So the orifice of the TOF would be, yes, exactly at that spot. So then we can really link it with what's reaching our substrate.
Another question. In the case of sputter systems where the substrate cannot be biased, is it possible to achieve similar effects by using a positive pulse after the primary negative hype impulse?
Yes, so then it's the bipolar hype impulse. So it's also, so I've not done so much bipolar sputtering, but from what I've read, that it is possible to then, instead of using a bias, to use this positive kick. Yes, absolutely.
I'll make a note,
But
Bob.
I can refer you to papers, so by Daniel Lundin, so from Lidköping. Then they've done quite a bit of work on bipolar hypens, so you can check out those works.
I also have a few papers from University of Illinois, have some nice research experimenting with the kick with these sort of time resolved diagnostic results as well. So I'll make a note. We can send those papers on. Okay, more questions regarding webinar attendance. Yeah, you get an email saying with all the links saying thanks for attending. So yes. How does duty cycle influence the rate and quality of deposited films?
Okay, so with higher duty cycle, so you have more on time, so you will, let's say, you will have higher deposition rates in essence. And then as for the quality, then it's, well, let's say it depends on many more variants than just the duty cycle. I mean, for instance, if you were to look at, maybe as an example, an aluminum nitride, so if it's a piezoelectric material, and then when you have oxygen incorporation, then those piezoelectric properties, then they drop, or they're no longer valuable. So of course you want to have higher sputtering rates so that you can decrease the amount of oxygen that's has time to get incorporated.
Caroline,
so in that sense,
can you show the slide which is where you have the copper, silver, and zirconium sputter rates? Because what I thought was interesting was it's not like a linear relationship with duty cycle, especially when it comes to hypems.
Yes.
It's actually
very material
dependent.
Yes, very material dependent. Sorry,
you found that
yes, there we go.
For copper, it was optimal at 50 microseconds.
Yes. Whereas for
the highest
zirconium,
deposition rate.
Yeah. Whereas for zirconium, then we can see that it's 25.
Yep. So you got to measure it. Oleg, hello. You ask, showing that silver creates much less ions arriving to the surface than copper. Was this an expected result? We can show you have the silver data.
Yes. So let me quickly go to. So I just move this box. Yeah. So we have high sputtering yields for silver, right? So we have a high density of those atoms in the region. Then what we do here is that, so what happens is that argon replaces silver. So we can only get so much, so we're limited in the current that we're able to obtain. And then, yes, so also with the ions, or the silver ions, not able to contribute to get more of these secondary electrons. So that's where we're limited. So due to that, we cannot reach higher currents, at least for our setup and our conditions.
There's another question. We get quite a few questions. Yeah, we have a few more minutes. So HIPIMS, the HIPIMS target, HIPIMS with a graphite target and an argon H2 mixture. And then he's asking what argon only, a time lag is expected due to the low secondary electron yield of graphite. Would you expect a decrease of the time lag with introduction of hydrogen?
Wait, sorry, if I go to the carbon data, let me take a look. Slide it was. Here, so here we didn't really have so much as a delay, just a slow rise. So here we just spotted with argon, so there was no hydrogen inside the film. At least on this examples, though I have done work where we were sputtering, but apart from argon, we had methane or acetylene, and we didn't observe any time lags in that case. It looked actually quite similar, the discharge or the waveform. I know, did I answer the whole question? I didn't see the, so I don't see the rest of the question.
The question is split in two, so if a little bit down further, it's
okay.
Yeah.
Yes, now I see it. If I introduce the decrease in the time, or well, I haven't seen it. Let me put it like that. But I didn't use pure hydrogen.
I guess the idea is that the hydrogen will travel faster, right? So lighter. Maybe. We have a little bit more time. Is this methodology appropriate while the discharge is excited in a hollow cathode effect? This is related to the duty cycles and the same sort of questions. I'm not sure.
I mean, in the sense of doing diagnostics, so then it's a bit, I don't know how confined it would be, or where you would place your probes. Or I know at least with hollow cathodes, or I've seen works done where they put so that would be in the context of generating nanoparticles that people have put in the quadruple mass spectrometer. But after it, so I don't know then if, no, to be honest, I don't know, but I believe there are ways, of course, to do plasma diagnostics for the hollow cathode. Because they are in that context, then no, it's for ARC that Anders did work, but for hollow cathode, or I can look up some papers. I think I have some, so in case I can forward them to Tom, or he can later distribute them.
There's a few more questions. We can maybe run over a minute, but we might not be able to answer all of them. One question is, what type of regulation are you using on your HIPIMS power supply? Average power, peak current, or something else?
Depends on the process. So for many of the processes, then I kept it at a constant voltage. So I wanted to see how the current changed. So I kept it at constant voltage. And other processes, I've done constant power. It really depends on kind of what aspect I'm interested in looking at.
And we'll do the last questions in the chat then. So is there any correlation between the occurrence of N2 plus ions in the OES spectra with the stress magnitude in the film?
I haven't measured the stress of those films, so I can't really say anything on that, but it could be an interesting aspect to look at.
How do you handle ion selectivity and measure it, for instance, to reduce the effect of gaseous ions in the substrate, like defect, stress, impurities?
So with that, so if maybe I can look. So this is the advantage of having the TOFA mess. Yes. So with it, then I can see which species are coming in when, right? So for instance, I know most of, so in terms when I do, for instance, microwave assisted processes, then I know most of, let's say, the ions or the argon or nitrogen ions, and they're generated in the microwave plasma, or they're constantly generated there. So for instance, if I wanted to limit that, then I would only have the bias on, let's see, during this section or just after the end of the pulse. Because otherwise I think it's a bit more difficult to really to limit it if you don't know exactly which species are coming in when. But with the TOF MS, or if you know exactly what masses you're looking at, you can use the quadrupole to then determine the timing.
And the last question is, can we learn a bit more about the TOF MS? Yeah.
Yes. So I also have a slide here somewhere. Yep. So is it? Yeah, if we just look at the TOF MS side. So so this is just this part that we're looking at just now. So if we have, let's say, a classic or TOF MS where we look at neutrals, then you would have first an ionizer. In this case, we're only sampling ions, so we don't have the need for this ionizer. And the ions get accelerated by electric field. So with that, they reach the same kinetic energy. And once they're at that energy, then the ions or the species that are lighter, then they will travel faster than the heavier ones. All right. And then with that, what we do, so we measure the time of flight. And then what we can do is that the time it takes them to reach the detector, so it's proportional. So like showing you, it's proportional to the square root of the mass overcharge of that species. So with that, we can then gather the entire mass spectrum during a single measurement. But for this, we also have a paper come out this year specifically on the eTOF MS, so I can also share that with Tom so he can later distribute that if you would like to learn more.
Yep, I'll follow up with all the questions with the papers, no problem. We'll gather them together. Right, so thanks very much, Caroline, for presenting, and thanks everybody for the questions. We will email everything out to the attendees probably tomorrow. So yeah, but let's leave it there. So
if you have also any more questions, feel free to contact me. I'll be happy to help out when I can. Yep.
Great. All right. Thanks very much. We'll leave it there.
Thank you very much, everyone. Thanks, Tom and Impedance, for organizing.
Happy to have you here. Thank you very much.